The Milky Way, our home galaxy. A glorious ribbon of stars smeared across the night sky. Almost unimaginably vast. Home to hundreds of billions of stars. And yet, just one of 100 billion galaxies that make up the observable universe. Galaxies are the building blocks of the cosmos. Within them, stars and planets form and die. The Sky at Night has covered every major space science discovery in more than 60 years of occasionally quirky broadcasting.
Line your finger up with my nose. It's absolutely tremendous. I'm going to do just a little mathematics. Please don't be frightened.
Now we're going to use that archive to tell the story of galaxies, from their earliest origins to their very end. And in the process, answer some of the biggest questions in the universe.
Good evening. Good evening. Welcome.
Welcome to the Sky at Night, Guide to the Galaxies.
Good evening. I want to begin by showing you a rather splendid picture. This is a galaxy, a system made up of thousands of millions of stars. And we must remember that we live in a galaxy. Our sun is a very humble member of the Milky Way system.
We take for granted today that the Earth and the solar system lie within a huge galaxy, and that galaxy is just one of billions of galaxies. But that knowledge was hard-won. Just 100 years ago, we didn't know for certain that galaxies even existed. Astronomers believed the Milky Way was the entire universe, and that nothing lay beyond.
And we have liftoff.
The quest to discover the galaxies has been the story of how we found our place in the cosmos. It's also the story of some of the most extraordinary technology ever developed. And it's led to some profound questions. Why do galaxies exist? What are the forces that shape them? And what will be their ultimate fate? The discovery of the galaxies begins around the start of the 20th century, when astronomers began to look more closely at patches of cloudy light in the night sky that they called nebulae. Telescopes had revealed hundreds of them, but one in particular became the focus of attention: the Andromeda Nebula. In 1978, the Sky at Night looked back at how Andromeda revealed the true nature of the galaxies.
I'm delighted to welcome to the Sky at Night, for the first time, but I'm sure not the last, Heather Cooper, who is lecturer in astronomy at the Caird Planetarium at Greenwich.
Without the powerful telescopes that we have today, Andromeda appeared to astronomers as nothing more than an irregular smudge. They couldn't figure out if it was just a nearby cloud of gas and dust, or something more significant.
Well, the mystery was solved by Edwin Hubble in 1923. He was using the then new 100-inch telescope on Mount Wilson, and he was able to take pictures of Andromeda, and he confirmed that the Andromeda galaxy was actually made up of stars and not gas. What was very exciting is that Edwin Hubble also noticed that there were some stars in the Andromeda galaxy which varied in their brightness, and these were the so-called Cepheid variable stars.
Now, a variable star is exactly what its name implies. It's a star which brightens and fades absolutely regularly. And the longer the period, the greater the luminosity. And you can certainly see the importance of that, because you can find out the luminosity of a Cepheid merely by watching it. And once you know how bright it is, then you can find out its distance. What Hubble did was to find Cepheids in the Andromeda spiral, study their periods, and find out how far away they were. And straight away he realized that they were so remote that they could not possibly be members of our own star system or galaxy, and therefore the Andromeda spiral itself must be an external system. And I think, it was probably one of the most important astronomical discoveries ever made.
In fact, it opened up a whole new field of astronomy, the study of extragalactic astronomy.
Andromeda wasn't a local gas cloud, but a galaxy like the Milky Way, a huge system of stars rotating about its centre. And once astronomers knew this, they realised that countless other nebulae must be separate star systems as well.
Most of those blodges you can see on the screen are not stars, but whole galaxies.
Now, the Milky Way was just one of hundreds of galaxies, each containing billions of stars. The universe had just got much, much bigger. But galaxies themselves remained mysterious. We still didn't know what types of galaxies were out there, how they developed, or even why they existed at all. As we set out to understand more about galaxies, it was inevitable that we began with our own home, the Milky Way. Our first challenge was simply to define it, its size, its shape, and its age. One of the first attempts to describe the Milky Way came when astronomer William Herschel produced a map that I got to see in 2017. This is the first map of the Milky Way made by William Herschel back in 1785 in a paper he called On the Construction of the Heavens. And it's a wonderful thing, but it's not accurate. It shows the sun at the centre, which is wrong, and there are no spiral arms. Over the next 200 years, astronomers gradually expanded their knowledge of the Milky Way. And by the 1980s, the basic facts were well established.
There are something like 100,000 million stars in our star system or galaxy. And the galaxy is a flattened system. And the sun, with its system of planets, lies well away from the centre or nucleus. In fact, over 30,000 light years away. We've also found out that our galaxy is a spiral form. And that's by no means surprising, because there are plenty of other spiral galaxies.
But there were still huge gaps in our knowledge. We had only a rough guess as to how many stars there were in the Milky Way. And although we knew it was a spiral galaxy, we didn't know how many spiral arms there were. Luckily, there were new telescopes on the way. Over the years, the sky at night has followed the development of many new telescopes.
This is the MMT, or Multiple Mirror Telescope, on the very summit of Mount Hopkins in the Santa Rita Mountains of Arizona. I am standing on top of one of the most remarkable telescopes in the world. La Palma is now becoming famous in another direction. It's here that one of the world's great observatories is being set up. Just look at it. It's short and squat, with a maze of wires and girders. It's the first of a whole new generation of telescopes.
Bigger and better telescopes were built above the clouds to lessen the distortion caused by the Earth's atmosphere. But still astronomers wanted more. To really see the Milky Way, we needed a telescope above the atmosphere.
Liftoff of the Space Shuttle Discovery with the Hubble Space Telescope.
The Hubble Space Telescope was launched in 1990. But unfortunately, when the first images came back from Hubble, they were a disappointment. It turned out there was a small but crucial flaw in the optics. In 2015, the Sky at Night looked back at NASA's attempt to solve this problem.
Repairing Hubble would require one of the most audacious space shuttle missions ever conceived. 5 long spacewalks would be conducted over 5 consecutive days. In terms of complexity and ambition, nothing like this had ever been attempted. To pull it off, the NASA astronauts spent over a year undertaking the most immersive training program to date. Telescope mock-ups were submerged in a neutral buoyancy tank. Logging more than 200 hours underwater, the astronauts repeated the hundreds of complicated maneuvers required to fix the telescope until they became instinctive.
5,
On the 2nd of December 1993, the mission to repair Hubble launched.
And we have liftoff.
So, Houston, let's go fix this thing.
Spacewalks are never routine, and the Hubble rescue mission was going to be harder than most. Back on the ground, the team at Mission Control held their breath. Carefully, astronaut Kathy Thornton maneuvered the new optical device into place.
It's a very big box going in a very small hole with about an inch of clearance going in, and then obviously the clearances got tighter.
Thankfully, it was a perfect fit.
Good work, guys.
But now scientists on the ground had to wait for the first images. On New Year's Eve 1993, they came in. What was a blur was now crystal clear, and our view of the cosmos was changed forever.
Hubble marked the beginning of a new era in the exploration of the Milky Way. Over the next few years, astronomers built up a spectacular catalogue of extraordinary objects.
It contains clusters, nebulae, colour stars, exploding stars, and even supernovae. I've been very impressed particularly by Hubble's pictures of Eta Carinii. Eta Carinii is a very, very massive star, highly unstable, and could one day, I don't know when, go off as a supernova. Look at this picture of the Helix Nebula, which is simply an old star that's thrown off its outer layers, and this material looks rather like a shower of tadpoles, doesn't it? Just shows the great power of the Hubble telescope.
The pillars of creation. That to me it symbolised the first of the Hubble images that started to come through that just gave this completely new vision of the cosmos. And it was just completely fascinating to think that this was what you could do with Hubble.
Well, undoubtedly, it's the most amazing telescope ever built, and it's now a complete and utter success.
Hubble's images took us on a virtual tour of the galaxy. My own personal favourite stop is this one. Our nearest stellar nursery in the constellation of Orion, where you can see new stars forming from collapsing clouds of gas and dust. It's just one image of one object, but it reminds me how studying the galaxies isn't just about abstract, distant theory. Each of us is a product of the processes that shape the galaxies. The Sun, the Earth, and everything around us came from just such a place as this. By the start of this century, we'd catalogued an enormous variety of strange and wonderful objects within the Milky Way, but we still didn't have a really accurate map of the galaxy. To get one, we'd need yet another new instrument. Enter Gaia, one of the European Space Agency's latest telescopes. In 2015, the Sky at Night visited the laboratory where its camera was made to learn a bit more about what makes Gaia so special. Gaia is a wide-field telescope designed to scan the entire sky. Instead of staring intently at individual objects, it's designed to give us a broad perspective. It's armed with two telescopes that focus light onto a sensor bristling with 1 billion photosensitive pixels.
What we have here is a duplicate of one of the imaging sensors that makes up the Gaia array. In the full array, we actually have 106 of these, and so it's pretty impressive. Each one of these detectors is quite similar to the sort of thing you'll find in a consumer digital camera, but with one difference. The pixels in this are much, much bigger. The engineers have worked out that with bigger pixels, we can gather a lot more light.
So much so that this sensor is capable of capturing more than 90% of the light that lands upon it, whereas my camera at home would be lucky to get 20%.
Gaia is expected to detect and measure hundreds of stars every second. And it will revisit the same patches of sky 70 times, which will allow it to do something extraordinary.
Not only will we have the most accurate map of our little corner of the galaxy, but also, for the first time, we'll record how the stars are moving. And that is a really powerful tool. Gaia took decades of planning before it finally launched at the end of 2013. But it was worth the wait. When the data came down, scientists were able to use it to construct a map like no other, a three-dimensional map of the galaxy. And in 2017, I got to see it for myself.
So, Chris, welcome to our new map of our Milky Way.
It's beautiful.
You see immediately the sort of big picture structure. First thing to notice is that this is a map of the entire sky.
But this stripe across the middle, this bright stripe, that's the galaxy.
That's the Milky Way galaxy, that's right. What we need to do is zoom in. So this is the top layer map, and now we're zooming in. So this is the inner parts of the Milky Way here, these big dust clouds and dust lanes, the dust lane. These are dust lanes, and you start to see that all the white light is now breaking up into stars, into individual stars.
As you get further in, as we zoom in, we see more and more stars individually.
Absolutely. Look at how they suddenly appear as you go that little bit deeper into space, and bang, what you thought was just white light is actually starlight.
And how many stars are there in the galaxy?
There's maybe 100 billion, 200 billion, 300 billion. What we know is that there's maybe twice as many as we previously thought.
How has Gaia doubled the number? That seems surprising to me. Where have they been hiding?
It's just because of the image quality of Gaia.
Because it can see sharply.
Exactly. Gaia can tell the difference between 2 or 3 stars that are very close together, but nevertheless are separate stars, whereas previously, from our images from the ground, blurry sort of things, this stuff here would have all been merged into what we thought was one star.
And so we've been looking at the map as it appears on the sky, but one of the exciting things about Gaia is that we have 3-dimensional information as well. We can go beyond this sort of 2-dimensional picture.
Exactly, and that's the unique feature of Gaia. Gaia measures distances as well as all these other things. And once we get into measuring distances, then we can measure the 3-dimensional structure of our Milky Way. So far, we've only just had a taster of that. So Gaia's just released 2 million accurate distances. And so here is the beginnings of a picture in 3 dimensions. This is our sun, and we're about to go and see the Hyades and the Pleiades cluster. And so here we are, for the first time ever, seeing a star cluster in 3 dimensions. So we can tell the difference between the front side and the back side. And so we have already discovered not only how deep the Hyades cluster itself is, but actually it's about twice as big.
It's amazing. What other features should we look for in this 3D map?
So this dramatic Hyades example, one very nearby cluster, is just a taster for what's going on. We've got good distances now for just 2 million stars. We're going to have 1 billion at least. That will give us a 3-dimensional map of half of our Milky Way. But even more interestingly, because Gaia's continuing to observe over time, it's telling us how everything's moving. And that combination of where things are and how they're moving allows us to determine how the galaxy works as a machine, how the Milky Way actually functions and how it's evolving.
Gaia's ability to map the Milky Way over time is vital, because our galaxy isn't static. The positions of the stars are constantly changing, but on timescales that we can't normally see. In 2015, I came here to the Peter Harrison Planetarium at the Royal Observatory Greenwich for a spot of time travel. Since humans evolved, they've been looking up at the night sky. But not the night sky that we see. This is what the sky would have looked like when the first humans emerged in Africa 200,000 years ago. And it's an uncanny sight. Some of the familiar constellations are there, but others are distorted beyond all recognition. And if we go back further, let's say to 1 million years before the present, then things change completely. The familiar constellations are gone, revealed to be nothing more than temporary, chance alignments of random stars. The view we have of the Milky Way today will be completely alien to our descendants. It will change dramatically over the course of the next 1 million years, becoming completely unrecognisable as the stars travel on their own paths, going their separate ways. Gaia is helping us map the past, present and future of our home galaxy in unprecedented detail. but it does even more. It's also revealing how the Milky Way is structured. I went to meet Gaia scientist Nicholas Walton to see the most accurate picture yet of the whole galaxy.
This is what our galaxy looks like top down. We thought we knew what our galaxy was like, but actually, because we're inside this very complicated structure, it's very difficult.
So this is our best guess as to what the galaxy might look like. The sun would be, I think, here, something like that. But interesting things happen near the centre.
Yes, towards the centre, you can see that the spirals of our galaxy come together. If you go in, we believe that this is a bar. And
this sort of straight structure at the centre.
This straight structure across here, and you'll notice that the spiral arms actually start at the ends of the bars. At the moment, we think that we've got a 4-spiral arm structure. A few years back, we thought we only had 3.
It's changing all the time.
It's amazing how the picture changes based on new information and new observations. This is an evolving picture.
It's humbling to think that after a century or more of observations, we could still be wrong about something as basic as the number of spiral arms in our own galaxy. What's more, Gaia is only just getting going. And it's now released a second batch of data, almost doubling the number of star positions and showing them in colour for the first time. Yet there's still one final mystery about the galaxy that needs explaining, and it lies at the very centre. Exploring what sits at the heart of the Milky Way ended up revealing one of the defining features of all galaxies. The problem is, it's almost impossible to see into the centre of the Milky Way, and that meant that for many years working out what was there required a fair amount of scientific guesswork.
When we look toward the centre of the galaxy, we can't see it because there's too much gas and, more importantly, dust in the way. And it's rather ironical, isn't it, that we know more about the nuclei of some other galaxies than we do of our own.
I think it's a real case of not being able to see the wood for the trees, actually.
Nevertheless, let's now go on a journey to the centre of our galaxy and see what we can find.
OK.
So let's speculate, shall we? What exactly is it? That's the $64,000 question.
More than 2 decades earlier, astronomers had detected something lurking at the centre, a bright, mysterious source of radio waves that we now call Sagittarius A star. But in fact, scientists suspected it wasn't a star at all.
If astronomers are right, and there is no direct evidence, then this extremely hot, superheated gas is spiralling into a massive black hole which forms the centre of our galaxy.
Yes. You know, I've a nagging doubt in my mind that some astronomers tend to introduce black holes every time they can't think of anything better.
Despite Patrick's scepticism, evidence that black holes existed was mounting. But understanding the role they play in the galaxy's evolution would take decades more work.
I think it's a good time to say something about black holes in general. So, what do we know about them? In theory, a good deal.
Black holes were thought to form when massive stars collapsed in on themselves.
Now, let's go to our old collapsed star. As it goes on getting smaller and smaller and denser, light cannot get away. And if light can't do so, then certainly nothing else can, because light is the fastest thing in the universe. So our old, collapsed, very massive star is now surrounded by a kind of forbidden area into which anything can go, but nothing, absolutely nothing, can come out. And that's what we call a black hole. Clearly, we can't see black holes. We can only detect them by their effects upon things that we can see.
For 25 years, astronomers searched the heart of the Milky Way for the telltale signs of a black hole, using near-infrared instruments to track the motions of stars around the very centre. It became clear that they had to be orbiting around something small but incredibly dense, with a very strong gravitational pull. It had to be a black hole, and not an ordinary one that forms from the death of a massive star. It was a supermassive black hole. We think that this kind of black hole forms early in the life of a galaxy, even before there are any stars. And it wasn't the only one out there. We now think that there are supermassive black holes at the centre of almost every galaxy. Black holes seed the formation of galaxies, and they control how they evolve. what had once seemed like science fiction was in fact a fundamental part of being a galaxy. As for how the Milky Way's black hole might affect us here on Earth, Patrick was on hand with some reassurance.
I think there's one point we ought to stress. There's no danger at all of the sun and the Earth and you and me being gobbled up by a black hole.
Absolutely none, because black holes only suck up things in their immediate vicinity.
Well, we told you it was like science fiction.
It feels like we're living in a golden age of discovery when it comes to the Milky Way. We may not have unlocked all of its secrets, but we know that it is 13.5 billion years old. It contains perhaps as many as 400 billion stars, arranged in 4 magnificent spiral arms that stretch 100,000 light years across. And it takes our solar system roughly 230 million years to make one complete rotation about the galaxy's center. But however much we learn, the Milky Way can only tell us so much about galaxies. It's a case study of one. To really understand galaxies, how they form, how they evolve, and what will become of them in the future, we need to cast our net wider.
All kinds. Some, for example, are spiral. There's a spiral galaxy, and of course our Milky Way system in which we live is itself a spiral. But then there are spirals of other kinds. There are these strange barred spirals, where the arms appear to come from the ends of a bar going through the nucleus. They're very strange indeed. Others are elliptical. Some have rather bizarre shapes. You can understand why that one's called the sombrero hat galaxy. Now, it was Edwin Hubble, after whom the telescope's named, who first worked out a really good idea of the classification of galaxies. And he produced what's always known as the tuning fork diagram for obvious reasons. There we have ellipticals, normal spirals, and barred spirals.
But these were just the basic shapes. To understand the full variety of galaxies out there, we needed to sift through and to categorize them. The problem? There are just so many. And so astronomers went in search of help from the public. In the old days, astronomers thought themselves lucky if they looked at 30 galaxies in their career. These days, we have literally hundreds of thousands of the things. No astronomer can possibly sort through them all, so we need to find new ways of looking at our data. We still want to care about each and every galaxy individually. They've all got their own stories. The only way to do this is to look at them, and amateurs have always done astronomy. They've discovered comets, supernovae, monitored the planets, explored the sky. What we did was we created a website which showed people some of these images, and we were just asking the simple question, is it a spiral galaxy with spiral arms and a disk, or is it an elliptical, a big ball of stars? Within 24 hours of launching, we were doing 70,000 classifications an hour. People told us about the weird things they find. The penguin galaxy, for example, yes, which is rather good.
There's lots that look like flowers. There's a whole thread of galaxy images that look like roses.
Or the alphabet, so we can write the sky at night in galaxies if we want to. We know that galaxies come in a whole menagerie of different forms. But what was actually creating all these distinct shapes? The quest for an answer led to some of the most complex and dramatic events in the cosmos. And at the heart of the story is a potent force that shapes all galaxies: gravity. In 2014, the Sky at Night went galaxy hunting on a quest to understand how gravity creates different types of galaxy.
One particular zone we've been looking out for tonight, just above the constellation of Virgo, is an area where many a time you wouldn't see too much detail in there, but get to a dark sky area like the Brecon Beacons and place a scope on this particular zone, and it comes alive wonderfully, and you can see exactly why this area is called the realm of the galaxies.
There are dozens, if not hundreds, of galaxies to look at with a small telescope in this area of the sky, and a bigger telescope will obviously show you more in something that's called the Virgo cluster. This image here shows us half a dozen bright galaxies, but then dozens more fainter ones, all different shapes and sizes. You can see elliptical galaxies that look like spheres, so we've got a close-up of a galaxy here, and it looks like a round spherical blob. There's not a lot of structure there. That's the combined light of billions of stars all glowing together. So it's quite a humbling thought when you think of that.
So if we take a look at the very familiar spiral galaxy, what would be the forces that would cause a galaxy to form rather like this?
Galaxies form from roughly spherical-ish blobs, groups, clumps of gas and dust, and they collapse under gravity. Now, if there's a preferred direction of rotation to that gas and dust, then that will settle into a disk, and that's what happens with spiral galaxies like this. The gas and the dust collects into this disk, and then new stars form, and we see the patterns we see today because of this axis of rotation.
Astronomers knew how spirals form, but just as interesting was discovering what was going on inside the spirals. To find out, you need to look through a range of different telescopes. Take M51, the glorious Whirlpool galaxy. Switch to a radio telescope, and we get a very different view. This remarkable image reveals the distribution of hydrogen throughout the galaxy. Hydrogen is the raw material from which stars are made, and this image shows that it stretches far beyond the main disk. But the radio image can't show us where stars are actually forming. For that, we need to switch to another wavelength, the infrared. What we can see in this image is light from more stars than we'd otherwise see in the visible. By using the infrared, we're able to peer through the dust that would otherwise obscure our view. And we can go further than that, and the colour here represents the different wavelengths of infrared light. The whirlpool itself has this brilliant red glow. That's light from the dust and gas, the fuel of star formation, which you can see is spread throughout the disk. But if you look along the spiral arms themselves, and only on the spiral arms, you see these bright knots, these bright blobs that are shining very brightly. They're places where thousands of stars are being born. So what this tells us is that it's not enough to have the raw materials for star formation. There's dust and there's gas throughout the disk, but it's only when it gets twisted up into these spiral arms that it can become dense enough to form stars. The spiral arms are where the action is. Spiral galaxies make up almost half of the star systems we see in the local universe. The spiral arms are areas of vigorous star formation, generated as the galaxies rotate. But what about elliptical galaxies? It turned out that the forces that create these are even more dramatic. It's a process we can investigate close to home in the interaction between the Milky Way and our nearest neighbour, the Andromeda Galaxy. The Sky at Night explored the key sequence of events in 2007.
The great Andromeda Galaxy, more than 2 million light years away. But it won't always be that way. It's coming towards us, and it's going to collide with our Milky Way. Not for at least 1,000 million years, but collide it will. It's going to be quite a sight. And I'm joined now by two eminent experts, Professors Carlos Frenk and Derek Ward-Thompson. Derek, Carlos, welcome back to the program. Good to see you again.
Hello, Patrick.
First of all, why is it coming towards us?
Well, at early times, thousands of millions of years ago, Andromeda and the Milky Way were closer together, and they started expanding away from each other as the universe expands. However, the gravitational attraction between these two galaxies is so strong, the galaxies have turned back and are now heading towards each other. So the very same force that caused Newton's apple to fall to the ground, that's bringing Andromeda towards us.
When will this happen?
That's an interesting question because we're not absolutely sure. We know it's coming towards us at about 100 kilometers a second. But what we don't know is exactly its sideways motion.
So the two galaxies will approach, but then will come into an orbit together. And as they orbit around, they lose energy, and eventually they will spiral in. And how long the spiraling in process will take depends on that.
That's the major uncertainty.
That's
right.
Yes.
Well, at the present moment, our Milky Way galaxy is a lovely spiral. And so is Andromeda, but when they collide, that will change.
That will change. These beautiful disks will be destroyed. The stars will be flung out, and then they will collect back together into a shape resembling a rugby ball, what we call an elliptical galaxy. During the collision, gas would have been heated up and ejected out of the galaxy. Once the train wreck is over, this gas will cool down and settle again into a new disk. So what started life as a spiral disk then went through a phase of elliptical galaxy, then might regenerate itself and grow a new disk. This has been going on for thousands of millions of years, and the galaxy can experience all sorts of morphologies throughout its life history. These collisions are the answer to one of the great riddles in astronomy, namely the process by which galaxies transform their identities.
The collision of the Milky Way and Andromeda will eventually create a new, giant galaxy. But it will be at least another 4 billion years before the merger is complete. It turns out that this intergalactic collision will not be a new experience for the Milky Way. Our galaxy is actually the product of many previous galactic mergers. The main disk of the galaxy is surrounded by a halo of stars and clusters which live both above and below the disk like this. But what's new is that thanks to Gaia, we can work out how this whole system is moving. Now, the disk is rotating. We've known that for a long while, so it's spinning in this sort of direction. But what Gaia has found is that some of these clusters are moving through the disk, and they're doing so in the opposite direction to the rotation of the disk itself. And so what that means is that these clusters are the remnants of galaxies which our Milky Way has accreted. Our galaxy is growing through galactic cannibalism. The Milky Way is not the only galaxy devouring a neighbour. Turns out that if you know where to look, the night sky is littered with similar scenes of cosmic carnage. From Earth, we see these events at a single moment in time. They take millions of years to happen, but we see only a single snapshot. These snapshots capture collisions at every stage of the action.
What have you got for us?
Nick?
Well, we're looking at an image of M51 at the moment and the interacting galaxy NGC 5195.
What do you reckon, Carlos?
I reckon it's just about to have its dinner, the big one. Snacking on this small object, and it's about to gobble it up.
Another good example of colliding galaxies is in Centaurus A. You can see it's quite dramatic. In the background, you can see a massive elliptical galaxy, but in the foreground, this incredible dark dust lane, it's actually the remnants of a spiral galaxy which is being torn apart. And it's actually thought that new images show a third galaxy having been shredded to some degree in the past.
When I started my PhD in the 1980s, this galaxy was a big mystery. Now we know that galaxies fall into each other all the time.
Where shall we go next?
And we can look at another popular target.
One of my favourites.
Wow, yes.
The antennae, NGC 4038 in the constellation of Corvus. You can see two distinct galaxies in there, but they're very, very heavily disturbed.
It's almost as if they're dancing around each other.
These ones have been caught in the act. They are in the process of merging. And this is one of the spectacular events that happens to galaxies of comparable size caught in the act of merging. And as Derek says, they engage in some kind of cosmic dance. And eventually they'll fuse together and produce one object after destroying each other in the process. But this is a beautiful image.
That's probably the most famous colliding galaxy in the sky. Let's go to some of the slightly more obscure but interesting ones.
Oh, wow, look at this. This is the
mice.
The mice.
Yeah, this is a Hubble Space Telescope image, I think.
These two could well be orbiting around each other, having already interacted once and torn out these streams of stars and gas from each other's galaxies and triggered new stars all the way along. You can see the tails are very blue, again showing us the characteristic signature of young stars.
This is very nice. NGC 6770, a nice pair of spirals.
I think that's right.
The two galaxies are not really heading towards each other, but they have a motion sideways, and so they orbit. And then the orbits don't last very long.
We should add, of course, that to a cosmologist, anything less than 1 billion years is fast.
Okay, well, I think there's one more image, so let's have a quick look at that. This is Stefan's quintet.
Cluster of galaxies, that's right, where two, certainly in the middle, are in the process of merging, interacting at the moment and dragging out tidal tails and all sorts of other interesting
There's some kind of
features.
promiscuity going on in here. You can see 5 or 6 of these objects engaged in some sort of indecent activity here.
Gravity shapes the way that galaxies form and interact. But what about the interactions of galaxies on an even bigger scale?
Galaxies are the units of the universe, and we want to find out about the distribution.
Surprisingly, when we look at the arrangement of galaxies in space, we start to see larger structures appearing. At the smaller end of the scale, galaxies collect together under the influence of gravity in groups. For example, the Milky Way is part of what's called the local group, made up of over 50 galaxies.
I know you've been making a close study of the local group, so first of all, what does it contain?
Well, as far as groups of galaxies go, Patrick, our own local group isn't terribly spectacular. It contains a couple of giant galaxies, like our own galaxy and the galaxy in Andromeda, a few medium-sized galaxies, like the Magellanic Clouds and the galaxy M33 in Triangulum, and a whole hodgepodge of small galaxies, tiny dwarf galaxies, which are scattered all around the local group. And here am I, standing inside the local group, and you have to imagine I've been blown up by something like 10,000 million times, and that gets me on the right scale. The local group is about 5 million light years across and has a sort of flattened distribution, as you can see around here.
We believe also that our local group is part of a larger association known as the supercluster, centred upon the group of galaxies in the constellation of Virgo, more than 50 million light years away.
Galaxy superclusters are simply colossal structures. But even they are not the biggest things in the universe. Superclusters themselves are arranged into dense threads that we call filaments, with huge voids between them. These filaments form a vast honeycomb structure, assembled from all the galaxies in the observable universe. For now, we know of nothing bigger. We now know a lot about how galaxies develop, but there remain profound questions to be answered. Where do galaxies come from in the first place? Why do they exist at all? And what will eventually happen to them? To find out how galaxies came into existence, we need to travel back in time, right back to the earliest years of the universe. In 1995, the Hubble Space Telescope captured a photograph that took us further back in time than had ever been possible before.
Now let's begin by showing you this. This is a recent picture sent back by the Hubble Space Telescope. It shows star systems or galaxies, some of them so far away that their light, travelling at 186,000 miles per second, takes thousands of millions of years to reach us.
The photograph in question became known as the Hubble Deep Field, and for my money, it's one of the most important scientific images ever taken. This one image gave us a way of seeing galaxies just a few 100 million years after the Big Bang. When it was first released, I remember staring at this image, almost unable to believe that each of these objects is not a star, but an impossibly distant galaxy. In 2015, I spoke to Sarah Kendrew to find out the story behind the image. So Sarah, tell us how the Hubble Deep Field came about.
The Hubble Deep Field, scientists had basically proposed to look at an empty patch of sky. So that's quite an unusual thing to want to do.
It seems crazy.
Right, because they had no idea what they were going to find. So it's quite hard to justify, but ended up being incredibly successful and became the iconic image for the Hubble Space Telescope.
It really is a stunning image, and we could look at it here. What exactly are we seeing in the deep field?
Every single point of light in this image is an individual galaxy.
But of course, this isn't the local universe, so we're seeing these galaxies as they were many billions of years ago as well.
That's correct. We're also probing down to the first billion years of the universe's existence, and that really was very new. It really gave us, for the first time, this quite large sample of galaxies from the very early universe. And we can take a closer look at them.
So the ultra deep field, which came a bit later, was sort of the improved version. But these galaxies look different from the ones we'd see today.
That's right, and that's one of the main outcomes of the Hubble Deep Field. Galaxies in the early universe, have quite a different appearance. Whereas the galaxies we see in the universe today tend to be quite ordered, they have a nice spiral shape, or they're blobby elliptical galaxies. These are much more irregularly shaped. So you can see, for example, some galaxies that are merging together. The universe was much smaller in those early days. So small galaxies were more densely packed, and so they would collide to then sort of form bigger structures.
It confirms the theory that it takes billions of years of mergers and collisions to form the large, regular galaxies that we see today. And it also showed that even early in the universe's history, galaxies were already forming. But it can't tell us why there are galaxies at all. To answer that question, we need to look at another, very different image, one that takes us even further back in time. This image shows the leftover glow from the Big Bang, the oldest light left in the universe, known as the cosmic microwave background. It's a picture of what the cosmos was like when it was only 300,000 years old, when there were no stars and definitely no galaxies. And so how did the universe go from this state to one where stars were organised into galaxies? In 2014, I spoke to Sarah Bridle to find out. We're going to talk about the early universe, which was a very different place from the one we see around us today. So what was it like?
Well, so early in the universe was much denser. So basically today we've got a vacuum in space, but if we go back in time to the early universe, the universe was much smaller. Everything was much closer together. Some patches were clumpier than others, so there was more stuff in one place and less stuff in somewhere else. We can see these red patches and blue patches. So where the red patches are, that's where the universe was hotter and denser, where it was really clumped together. But the blue patches here are where it was cooler and more spread out. So in fact, those hot patches where there's lots of stuff, that would have then gone on to form the first stars and galaxies and that we can see today.
The cosmic microwave background shows the first tiny density fluctuations, the seeds of what will eventually become the galaxies. But there was a problem with the physics. There wasn't enough matter in the early universe to account for the clumps that we see. There has to have been something else there, giving an extra gravitational pull. We're still not sure what this something else was, but we give it the name dark matter, and it's thought to be crucial in forming these first clumps, the seeds of galaxies. Unless we can understand and detect dark matter, we can't explain how the stars and the galaxies came into being. But the problem with dark matter is that it doesn't normally interact with anything except through gravity. That makes it almost impossible to detect. Despite looking for more than half a century, we still haven't found anything. Our best hope is to look for the rare instances where a dark matter particle collides with a particle of ordinary matter, creating a very faint signal. The search for dark matter is one of the great quests in science, and it's led to the creation of some suitably impressive research facilities. I went to see the latest state-of-the-art equipment that's searching for dark matter early in 2018. This is Gran Sasso in the heart of the Italian Apennines. But we're not here to admire the view, we're heading underground in search of dark matter. This is amazing. We're driving down a secret tunnel underneath a mountain, just like in a James Bond film. But this is where physics gets done. I met up with Rani Budnik, who showed me the experiment that he's working on.
This is the xenon experiment.
This is amazing. This place is enormous. The lab is underground to escape from cosmic rays, high-energy particles that rain down on us from space all of the time. Down here, there are 1 million times fewer than at the surface. Vital if scientists are going to have any chance of spotting the subtle signals of dark matter. That's the job of Xenon 1T, a detector filled with 3.5 tons of liquid xenon. The theory is that just occasionally, a particle of dark matter will collide with a xenon nucleus, and that can be detected.
What we're looking for is basically kind of a billiard ball interaction. Our xenon nucleus basically is being kicked. This particle gets some energy and then deposits the energy inside our detector.
Okay, so you're looking for these direct hits.
Exactly.
These rare cases when a dark matter particle happens to hit directly a xenon nucleus.
Yes.
Well, that's the cheerful possibility. You could press the button and see nothing.
Exactly. This is actually what usually happens, or what happened all the time so far.
Hundreds of scientists have spent a decade looking for dark matter at Gran Sasso, and they're still looking. So for now, our best understanding of how dark matter helped create the early stars and galaxies comes from computer models. In 2015, Jim Al-Khalili went to meet Andrew Pontzen to see the latest model in action.
We think dark matter had a crucial role in making the universe like it is today. So I can actually show you here a simulation of the way that dark matter behaves. Because it's in a computer, we can paint the dark matter any color we like. We can make it visible. So I'm going to paint it green and show you what happens over the first 1.5 billion years or so. So I can hit go. Then we've just seen the Big Bang. The whole universe, or at least this chunk of the universe we're looking at, is expanding. And as it does so, you're seeing what happens to the dark matter over the first 1.5 billion years or so. It started out quite evenly spread out, coming towards us, but over time, it forms into clumps.
So, of course, this is the dark matter which we wouldn't be able to see. How does that relate to the visible universe?
Yeah, we can switch views and show what the computer thinks the visible universe would look like at this time. Every dot of light you see here is a forming mini galaxy. It's got maybe a few million stars in it. But the key thing is that they wouldn't be there unless the dark matter is there in the first place. It's that extra gravitational pull that all that dark matter is providing that pulls the gas in and allows it to sit there and start forming stars and start forming the galaxies we know today.
The important point, they're clumping together not because of their own gravity, although that must be important, but because of the gravity of the dark matter, which is much more dominant.
Yeah, that's what we think the key role of dark matter is, to pull all this stuff together and actually clump it into something that can form these galaxies.
How does that evolve? What does it look like today?
Well, we can use these computer models to work out precisely that. If I switch to another view, here we've zoomed in on one of those single points of light that you saw. This is going to turn into something like our Milky Way galaxy today. So if I restart time, then what you see happening is all these different little mini galaxies start merging together. And once again, we think dark matter is playing a key role in this. It's the gravitational pull associated with the dark matter that actually pulls all these different bits and pieces together and starts assembling the present-day Milky Way, which just grows and grows.
We think we understand how the galaxies appear after the Big Bang, but there's one big question left to consider, perhaps the most important of all.
What about the future? Will the universe end? What's going to happen to it? It's now 70 years since Edwin Hubble discovered that the universe is expanding. All the groups of galaxies are racing away from all the other groups, and the expansion is universal.
Understanding this expansion of galaxies away from each other is the key to their ultimate fate. The question is, will the expansion continue, or will it eventually stop? In a universe with just normal matter and dark matter, gravity should be able to slow down the cosmic expansion. There's just one problem with this theory. That's not what we see happening. Gravity isn't slowing the galaxies down. On the contrary, something else is speeding them up. And the question is, what's causing this acceleration? Jim Al-Khalili went on a quest for the answer.
Well, the truth is, we don't know. But at least we've given it a name. Dark energy. A weird new force that pushes the universe faster and faster.
The fate of the galaxies, and indeed the entire universe, comes down to a straight fight between gravity and dark energy.
Without dark energy, gravity is the most significant force dictating the fate of the universe.
If gravity is the dominant force, then it means that one day the universe might stop expanding and start contracting. Eventually, it'll collapse together in what's known as the Big Crunch.
But if dark energy turns out to dominate, then the end of the universe could be much lonelier. As the universe spreads out, the influence of gravity becomes weaker until everything's too far apart for it to have any effect. Then, dark energy will be the only player in town.
As dark energy keeps pushing the universe apart, eventually all galaxies will move so far away they'll become invisible to each other. The distances between them will become so great that light from one would never reach the others, and the universe will disappear into darkness forever.
So, what's it going to be? The truth is, we don't really know what dark energy is, and so we don't know how the story of the galaxies will end. We've seen back in time to their earliest origins. We've discovered how they grow and change. And we've seen the most astonishing events and structures inside them. It's quite an achievement. Not bad, considering that we've worked all of it out from here, on a tiny observation post in an obscure corner of the Milky Way galaxy. We may not yet know the whole story of the galaxies, but even without an ending, it's already clear what an epic story it is.
And for another epic space story, don't miss the feature-length documentary The Last Man on the Moon on BBC iPlayer. Here on BBC4, missions continues as the crew struggle to make sense of their discovery on Mars.